Now we will do potential due to dipole. Potential due to dipole. We take the first position. Point on axle line. Okay, it's a dipole minus Q plus Q. This is L, and this line is known as axle line. On this axle line there is a point here, and this point is at a distance r from the dipole. When we say r from the dipole, that means from center of the dipole. Okay. Now we have to find out potential at this point P. V due to minus Q is equal to, tell me how much it is. Q upon minus Q upon, what is the distance from this point to this point? This is R plus L. And V due to plus Q, this is plus 1 upon 4 pi epsilon naught Q upon, what is the distance of the plus Q? R minus L. These are the potentials, and how to add them? It's not a vector quantity, scalar, simply add it up. So V is equal to V1 plus V2. This is equal to, what is common? 1 upon Q upon 4 pi epsilon naught. This is common, and what we get inside? Positive first, 1 upon R minus L minus 1 upon R plus L. Okay, please do it. Clear? Okay. Now Q into 2L is what? P. So we can write it 1 upon 4 pi epsilon naught P upon R square minus L square. This is our formula for potential at distance R from a dipole. Okay. In this case, if dipole is very small, length is small, and the distance r is very large compared to length, then we can neglect L square while subtracting it from r, and in that case, if L is much smaller than r, then V is equal to 1 upon 4 pi epsilon naught P upon R square. This. Correct? So this is potential due to dipole on the axle line. What was the potential due to a point charge on a line? That was 1 upon 4 pi epsilon naught Q upon R. This is R square, mind it. Now, out of this R and R square, there is one question. A single charge is having potential. A dipole is also having potential at this point. When we increase the distance, which potential deplete faster? Again, potential due to point charge goes on decreasing. with the distance. Potential due to dipole also goes on decreasing with the distance, which depletes faster. कौन जल्दी weak होता है? How do you know? Because it is proportionate to 1 upon r square. If the distance is made 3 times, then for point charge it will decrease 3 times. But in case of dipole it will decrease 9 times. So it depletes faster in case of dipole. Okay. Now we come to another charge distribution, that is same charge distribution dipole, but another situation. That is, we will take the point P on equatorial line. P on equatorial line. Here is point P and the distance is r. This distance is r. L, L, 2L. This is the dipole. Okay. Now, at P, V due to minus Q is equal to 1 upon 4 pi epsilon naught negative minus Q upon this distance r square plus L square half. Potential due to plus Q at the point P is equal to 1 upon 4 pi epsilon naught, and this will be plus Q upon r square plus, this is also again r square plus L square to the power half. Therefore, net V zero, right? Because it's a scalar quantity, direction, there is no direction. There will be a simple addition of plus potential and minus potential, and this will become 0. So remember, in a dipole there is 0 potential. Where? Along the, yes, and this is very, very important question. So many formulas you will remember, and you will be asked in a system of charges, where is the potential 0? What is your answer? On the equatorial line of a dipole, the potential is 0. Nowhere else it is 0. If it is asked in a system of charges, where is electric field? 0. Nowhere. Anyway, you will come to know, search all the things, you will find it out. Inside the shell, that is there. Inside the shell, but there has to be a shell. Okay? Not individual charges making a system. Right. Okay, we will find out electric field is 0, because if there is two positive equal positive charges, then just at the center of the two, how much is the electric field? 0, right? But that is only at the center of the two. At this point, E is 0. But if you go little above or little down, you will find electric field is there. Correct? Because this will make electric field in this direction, this will make electric field in this direction, and you will get a resultant here. Resultant will be there. Where this resultant is 0? Exact at the midpoint joining the two charges. There you will find electric field 0 and both the charges should be similar. Correct? So this is where E is 0. Now we come to a general position of the dipole. We have done two positions, potential on the axial line, potential on the equatorial line, and now we will do potential at any general condition. Okay, we will make it a bit larger for sake of calculation. Here is any general point P. We have to find out potential there. So we join it with plus Q and we join it with minus Q. The distance of P is R from dipole. Where is the R? Answer is the distance is always carried from the center of the dipole. So here is the center. And this R. This is L, this is L. Okay. Now what we do, make a perpendicular from here and make a perpendicular on extended R. This. What is the location of P? We must define it. What is the direction of P? Vector, dipole moment. Answer from minus to plus. This is the direction of P. What is the direction of position vector R? This. Angle between the two, theta. P is a point at position vector R making angle theta with position vector with P. Is this situation clear? Okay. Now we have to find out potential at P. V is V due to minus Q, V due to plus Q. Correct? This is the strategy we were doing in all other cases. We will do it here also. Now, we want to find out this distance because we have to place it Q upon R. This is the distance, how much it is. This distance is R, this distance is L, this is theta. How much is this distance? Can you tell me? This is theta. Let us say this distance is X. X upon L is what? Which trigonometric ratio? Cos theta. What is this? X upon L is cos theta because this is right angle. Correct? So, what is X equal to? L cos theta. And what is this X equal to? Again, this is also L cos theta. L cos theta, this is also L cos theta. This and this. Now, this total length is how much? R. Out of this, you cut this portion L cos theta and this will be almost equal to this. ये समझ आया? फिर से देखिए, this is an triangle. These two sides are equal, and this. If I want to ask you how much is this length, you will say this length minus this length, correct? And how much is this angle? If this angle is very, very small, approaching 0, then this each angle is almost 90. So whenever we want to find out the difference between length of two lines, what do we do? In दोनों के बीच कितना difference है? How do we find the difference? We don't measure each line separately. We don't measure each line separately. What do we do? We simply cut this line along this. These two are equal. This is the difference. Understand? How much is this line? If this line is 10 centimeter, this is 2 centimeter, then this is 10 minus 2. The same thing we apply here. How much is this length? Now we understand. This is R minus. And how much is this? Correct. Now we can make it. V is equal to V due to minus Q minus 1 upon 4 pi epsilon naught Q upon R plus L cos theta plus V due to plus Q 1 upon 4 pi epsilon naught Q upon R minus L cos theta. This is equal to Q upon 4 pi epsilon naught, and here positive first, 1 upon R minus L cos theta minus 1 upon R plus L cos theta. Okay, this is equal to Q into 2L is P. This is our answer. We can simplify it further. If L is much smaller than R, then V is equal to 1 upon 4 pi epsilon naught P upon R square cos theta. This is at any general position. Now we can check this on coaxial line. What will be theta? 0. So cos theta is 1. 1 upon 4 pi epsilon naught P upon R square. This coaxial line. On the equatorial line, theta is equal to 90. So cos 90 is 0. The whole thing becomes 0. Right? So this is the general formula. So this what we have done is potential due to a distribution known as dipole. Equipotential surface. There is a charge here, source charge. It is having electric field all around it. Let us assume a surface in the shape of a sphere or a spherical shell and it has got radius r everywhere. Okay. Now, what should be the potential at this point? Answer C q upon r. Here C q upon r. Here C q upon r. Everywhere we find the potential is same. Now, if I put a charge here, test charge, will it go towards this point or will it go towards this point? Answer, the charge has to move from higher potential to lower potential, and in this surface the potential is same, so it will not move at all. This surface, on every point of which the potential is same, is known as equipotential surface. Any surface on which at every point the potential is same is known as equipotential surface. This may be a real surface, this may be an imaginary surface. Okay, so we will write it equipotential surface. Equipotential surface. This is the equipotential surface. Here the potential is V, here also the potential is V. If I bring a charge from this point to this point, how much work has to be done? Suppose here is the charge, we put it and we bring it here. How much work has been done? The answer is, it is a work in electric field. Electric field is a conservative field, it's a conservative force, so the path does not matter. What matter is the displacement. Okay, now we take this displacement from this point to this point. This is the displacement. If you bring a charge Q from this point to this point, how much work is done? The answer is, we know potential and work, how they are related. Work from B to A per unit charge is equal to VA minus VB. And in this case, how much is VA minus VB? VA minus VB is 0. Why 0? Because VA is equal to VB, it's the equipotential surface. So, work done is 0. Is 0. This you will remember, and it is not affected by the path. This is equipotential surface. Now this equipotential surface has certain potential. The potential is not zero but equal at all points, but it has some. That means if here potential is 100, here also it will be 100, here it will be 100, here it will be 100, everywhere it will be 100. Now see here. It is an equipotential surface. The distance is very less and it has a potential of 400 volt. Now at this distance with this radius there is another sphere. This sphere is also an equipotential surface and its potential is more than this or less than this? क्या पढ़ रहे हैं आप इतनी देर से? If the distance increase, yes, correct, the potential will be less. This is another equipotential and this distance is larger here. So this is an equipotential surface, this is an equipotential surface, this is an equipotential surface. There can be a very large number of equipotential surfaces. All these surfaces will be known as equipotentials. Equipotentials. Equipotential क्या होती हैं? इक्विपोटेंशियल सरफेसेस. अच्छा, अब ये इक्विपोटेंशियल सरफेसेस, इक्विपोटेंशियल्स कैसी होती हैं? थोड़ा इनकी जस्ट इमेजिन हाउ डू दे लुक. दिस इज अ स्फीयर, द अदर वन इज अगेन a sphere. These two will be parallel to each other. This is again parallel to each other. That is again parallel to each other. So equipotentials are always parallel to each other. Okay. Equipotentials are parallel to each other. Parallel surface. Okay, now another thing. This radius, it has got two indications. Number one, because it is radius and it is surface, what is the angle between them? Correct? At right angle. Another thing, here is the positive charge or the source charge is placed here. What is the direction of electric field radiated by a point charge? Answer, it is radially outward. So this is the direction of what? Electric field, E. Now if this is the direction of electric field and this is equipotential surface, what is the angle between them? 90 degree. So this rule we remember, that at any location the direction of electric field and equipotential surface are at right angle to each other. ठीक है? So now we got a relation between the two and this will help us to imagine equipotential surfaces, because equipotential surfaces are at right angle to electric field lines. right? If we know electric field lines, we can create equipotentials, and if we know equipotential surfaces, we can always draw electric field lines. If I tell you that these are two surfaces which are equipotential, this is V100, this is V150 volt, all places. What is the direction of electric field? Answer, it must be perpendicular to both. So here to here we draw this line. This is the direction of electric field. This. Where should I put arrow? Upward or downward?
Downwards.
Why?
Potential.
Very good. The potential decrease along E. Okay? So here high potential, low potential. So this is E. And how much is this angle? 90 degree. 90 degree. This is the relation between the two. Okay. Now on the basis of this, we will draw certain equipotentials for different charge. Like this is point charge. And this is direction of electric field. Where should be equipotential? Okay, I tell you, take equal distance, right angle, equal distance, right angle, right angle, right angle, right angle, right angle. All distances are equal and make a sphere. At everywhere V is same. This is equipotential surface. So this is equipotential surface and this is electric field. Like this. Understand? Okay. Now we go for different shapes. Like if we ask you, there is a dipole and there you find out equipotential surfaces in a dipole. How to draw equipotential surfaces in a dipole? Any shape which is given to you, first draw electric field lines. If you know. Okay. Electric field lines start from positive and at negative. This. Right angle to this, right angle to this. This way, this. Okay, these are what? Electric field lines. Now we have to draw equipotential surface. See here, plus minus 90 degree to this, 90 degree to this, 90 degree to this will be the equipotential surface. This. This is equipotential surface, but now at equipotential surface, the potential should also be same. Because of this minus, here there will be negative potential, which will be less here, more here. So what we find that here the equal potential will be this way. This is the equipotential surface here. Now let me correct it. Where is the zero potential? Minus L distance plus L distance. Here potential because of this will be how much? Minus Q upon L. Because of this how much will be? Plus Q upon L, add the 2, it will become 0. Here potential is 0. At which other point it is 0? At infinity. At infinity. So this equipotential surface will go like this. It will not bend anywhere. Where it is going? Infinity. Okay. Then the next equipotential surface you will get is for case of plus and minus. You will keep the distances close here. ये इससे ज़्यादा दूर करिए. फिर and on the right hand side they will keep on increasing. This. And this will go here. और ये कहाँ गई? Infinity. समझ आया? इसके बाद वाली इधर से ये, इसके नजदीक वाली ये, दिस. इधर के डिस्टेंस बड़े होते जाएंगे, इधर के डिस्टेंस छोटे छोटे हैं. सेंटर में कैसा पोटेंशियल है? 0. This is equipotential straight and these are equipotentials curved. Okay, you can make it a bit smooth. So what are the white lines? Electric field lines. This is E, and what are these? Equipotential surfaces. This is for what? Minus Q plus Q, dipole. Plus and minus. Okay, now we will see another example, and that will be both charges are similar, plus plus. Plus and plus. In this, mind here, these are nearer, these are far away. These are getting away and here these are nearer. ये दोनों एक से उल्टे होंगे, reverse to each other. Then finally they become totally separated. Here finally they become equal, because if we see it from the distance, what will appear to us? There is a bundle of positive charges lying here. Bundle of positive charges like point charge. So this is their equipotential surface, just like a sphere. Here, if we see it from the distance, plus and minus will make zero charge, and zero charge, there will be no equipotential surface. So this is the difference. You must remember all this. Sometimes it is asked in the examination, make out equipotential surface for such things. And remember the principle. What is the principle? Make electric field lines. Make electric field lines. Here, what are the electric field lines? The electric field lines are like this. These were electric field lines. See, perpendicular, 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 perpendicular. No electric field lines. This become constant here. Here white are electric field lines. Here white are electric field lines. E, E, and this red one is equipotential surfaces. Okay, now final thing for equipotential surface. What we have learned so far, equipotential surface and electric field lines are at right angle to each other. Other thing is, any charge taken from one point to the other point on equipotential surface, the work done is zero. We don't have to do any work. Third thing, if at any point a charge is placed and it has got higher potential compared to other point, then it will try to move from higher to lower potential. That means on equipotential surface, the charges do not move. Even if it's a conductor, even if they have liberty to move, they will not move because potential is same. Now take this principle reverse. If there are charges on a surface and they are not moving, what does it prove? The surface is equipotential surface. Now we have taken this metal plate. On this metal plate we have given the charges. The charges distribute themselves because of force of repulsion and they settle themselves. After that they stop moving. When they stop moving, then what do they prove? That all should move if there is a potential difference, and they are not moving. What does that move? The potential has become equal. So we remember, any metal surface is an equipotential surface. Please write it down. It's very, very important. Any metal surface is an equipotential surface. Metal or conductor. This is electric field and this is equipotential surface. they are at right angle to each other. If they are at not right angle to each other, prove that E is at right angle to a conductor. ये इसका एक छोटा सा प्रूफ है. इफ इट इज, देखिए प्रूफ क्या है. इफ इट इज नॉट एट राइट एंगल, देन let it make theta. Yeah. हमने सोचा कि इलेक्ट्रिक फील्ड सरफेस के साथ कितना बना रहा है, थीटा. देन इट विल हैव टू कंपोनेंट्स. वन इज दिस कंपोनेंट along this surface, that is E cos theta, and one is this, how much, E sin theta. Then E cos theta is along the surface. It will apply force on a charge. F is equal to Q E cos theta, due to which charge move. Due to which charge move. But on the surface of metal we find no charge is moving. मेटल में कोई भी चार्ज एक जगह से दूसरी जगह नहीं जाता, उसमें करंट नहीं फ्लो हो रही होती. सो सिंस चार्ज इज नॉट मूविंग, F इज इक्वल टू 0. अगर चार्ज मूव नहीं कर रहा तो उससे क्या पता लगता है कि उस पर फोर्स क्या है, 0. अदरवाइज नेट फोर्स शुड ऑलवेज एक्सेलरेट और मूव ए पार्टिकल. तो अगर वो नहीं मूव हो रहा है तो F क्या है, 0. एंड हाउ मच इज दी F? therefore Q E cos theta is equal to 0. Now Q is not 0, E is not 0, then what is 0? Cos theta is equal to 0. Therefore, how much is theta? Yes. इसलिए थीटा कितना होना चाहिए, 90 डिग्री. Therefore, electric field is always at right angle to the surface. ठीक है, ये एक छोटा सा प्रूफ है, बहुत कम पूछा जाता है, बट देयर इज ए प्रूफ. और इसके बेस में क्या है, द चार्जेस अलोंग द सरफेस आर नॉट मूविंग. दैट शोज इलेक्ट्रिक फील्ड हैज नो कंपोनेंट along the surface. No component along the surface means it is normal to the surface. Okay, so this is all about equipotential surfaces. The metals are always equipotential surfaces. पर अगर हमारे पास एक रेफ्रिजरेटर है या एक मेटल की कॉम है, उसको जब हम बॉडी पे टच करते हैं, लाइक दिस, इफ वी टच इट हियर वी डू नॉट गेट एनी शॉक. If we touch it here in the corner, we get the shock. Potential is same. Why do we get a shock here with the same potential? Okay, that is a different phenomena. We will study in the next class. Okay, so we'll close it today.